Today we're going to see this system that you see on the screen, and we are going to understand how derivative causality occurs, what can we do to fix it, and how can we do to understand what in real life it means. What does it mean on a physical system to have derivative causality? And when you propose a solution, also, what does it mean mathematically when we do a solution for an equivalent system or any other solution such as solving implicit set of equations? So let's get started and look at first at this normal system that you see in there. And it's very clear here that we have a CAM follower system. What is the model of a valve on an internal combustion engine? And this is in here you have on the left hand side, you have this lobe, you know, that the CAM has. A CAM has a lobe, it's not just a circular body, but one that is intentionally built in here so that when this rotates, this would lift up. So this is lift up, and the motion would be carried through this push rod to this little part in here that is a rocker arm. And then you have this valve, which is the valve that could be an intake valve or an exhaust valve. Sits on here on the edge of the main pole of the body of the head of the engine, and it is this valve that when it's pushed in here lets the air in here if it's an intake valve, or lets the air out if it is an exhaust valve. So our task is to do a computer model of this. And what I'm going to do is I'm going to take advantage of the fact that we have this model, which is very obvious. You have it on the right hand side in here, and we have the tappet over here, and then this push rod model here with the stiffness and damping. We have the rocket arm model as a rotating mass in here, and then you have the valve itself on the right hand side. I guess I was fortunate that when I was little, I had the opportunity to see this in real life. And my father was an auto mechanic, so I saw the system taken apart many times and actually play with these parts and since I was a kid. So, any case, you see there is a step between this real system and this engineering model or this idealization of what the real system is. So what I would like to do is to go over the different possibilities of doing this transition. So let's see if you can perhaps see this a little better here. Uh, there you go. We have this rocker arm, which is represented over here, and you have this see this valve, which is represented over here, and the push rod over here like this, with damping and stiffness for each one of those to allow for the um, adjustments between the parts and the friction as well as the damping and the some of the stiffness of each one of the parts. So the computer simulation, the computer model that we can make over here on this end, we can just draw it bone graft model on the screen. And I'm just going very quickly to remind you of that procedure and actually do it right here on the screen for you. So why don't we just maybe do this and allow this to write on this screen here. I could do it right on the model itself. And how do we start? We put a one junction for the velocity of each one of these. Put a one junction for the rotation of this one. Put a one junction for this mass as well. Put a one junction for this. Put the one junction over here like this. And then a one junction for a reference over here. So we could just build our models in here based on this right on the physical system. We have done the first step of the procedure that we have outlined for several other models. First, write one junction for each distinct velocity. Then we attach the elements that see those velocities. Like, for example, in here you'll have a source of flow. In fact, this is velocity equals to 0, this reference over here. You will have the I element over here. In this one, we have the I element over here for the rotation as well. You have an I element over here for this. There is the I element of this. Then you have an I element for this one also. Okay. And then we would use the elements for the relative velocity in here by using zeros. Let's say O. And here there was also an input, a source of flow, which would be the velocity at this point over here. But in between these two, we have the difference between these two velocities, from which we have seen that we can put the C and the R element on this. The difference is seen again by the difference between these two. You see one like this with the C and the R element. And we keep doing the same thing for all the others because that structure repeats itself. So this would be like this, like that. Let's continue with the rest of the models here. On this you will have another 0 here. And then, of course, with this one here with the C and the R element over here, you have another one in here with this. See, I mess up. I needed a one junction here for this velocity and another one for this other one. So I just, we have this one in here with the C and the R element like that. And then in between these two, there is a transformation between those two because there is the modulus A over here. And between this, that is omega in here, you have another TF like this. And wow, you believe we're done with this? Yes. Okay. So what we can do is enter this into the CAMG software and do this like this, see? So the one I just did, take a look at this. This is the bone graft model. It's the same one that I have over here, this one. See? Okay. once this is entered into CAMG, everything is cool. No derivative form, no nothing. Everything is fine, normal. We have idealized the system in such a way that we have the one inertia for the rotating, for this rocker arm. We say, okay, look, this is like a bar rotating about a fixed point with its moments of inertia here and I element in here. So this I element, in fact, models the entire bar in here. Yeah. So I think if you look at it in this, yeah, this I element models this entire rocket arm like that. Yeah. This entire bar like that. But I am pointing it out because in order to understand derivative causality, what I did is I started with a system that is totally normal. I didn't start with a system that had problems and then try to see, you know, what we can do. But rather, if I start with a normal system and I change it, I can then discover and understand better why derivative causality occurs. What I'm trying to say is that, let's say, well, this is the same bond graph, but I put the names on each one of the elements, but that's the same one. What I'm trying to say is that, what about if we represent the system this way? Huh? Is it different? Is it something wrong by doing this? You see, before I had one single mass. In fact, if you're still looking, see right there was one of them. But now, instead of doing that, I am doing this. So instead of representing the mass at the top with one single mass, I did it with two, with a massless connecting, bar in here, and with the two masses right there. Okay, so if this is the case, this one is in derivative form, which is the corresponding to this. Okay, let's think about it for a second and reflect as to why it happens. And this reflection would reveal to us that if we idealize the system and we represent, or we made the transition of the system from reality to this model, it's very obvious that in here, if this mass goes down, this one right here, if this goes down, this one has to go up, right? If this one goes down, the other one goes up. What does that tell you? It tells you, look, the system has only one possibility. This goes down, this goes up, this goes down. That means the motion of this one is depending on this one, right? Or vice versa. When you have a situation like this, where you think there is two masses, in fact, this is telling you, one depends on the other. So in reality, maybe there's only one mass, just like it was. But in this case, illustrates that if we model it this way with two, we will end up with derivative form. Or we represent the system with a rotational inertia and represents the entire bar like that, like we did before. Or we can do it with these two but in this case, there will be a derivative form on the right-hand side. That's the element over here, like this one. So the conclusion is, if you if, if you see a system with derivative form, you should question, is there an equivalent system without derivative form? Okay, that would be a way to solve this, and also would be a way to review your model and and see if in fact maybe you shouldn't have too many eyes. You should have maybe only one instead of two. And so, okay, fine. If we do this and you end up with derivative form, if you have two, take a look here now. We took off the one on the right hand side. We took off this one, and now we only have this one on the left. Question, is the system the same? Did we mess it up? No, we did not. The only thing is that we found an equivalent system. We found an equivalent representation of the system. But this one does not have any derivative form. So we found this, and this would be just fine. Everything is fine. Now, in order to produce an equivalent system where we only have one mass on the left-hand side over here, we need to make sure that the effect of this mass, in fact, does the same thing as the two that we had before. In order to do that, we need to find an equivalent system that where the kinetic energy at the point B is the same as the kinetic energy of some mass equivalent at A. Okay, so the kinetic energy of this one that was in here should be the equivalent of some mass on the right hand side. We know that the relationship between the velocities of A and B is like this through the lever ratio, and that the mass B placed at A would be an equivalent mass because, right here, if you take it from this, the equivalent would be, M equivalent would be MB times BA square, BA square over V, which would be this, and then B this square. So this one over here, this I, will have to be the original one that was at A plus some equivalent mass that it used to be here at B, but now we move it to A. So the system in this case is completely equivalent, but it is no derivative causality. One thing that we should point out is in case that we have a derivative causality, CAMG is going to give us a warning. This is red, as you see in there, showing the derivative form. But now I think we should go into finding out how to fix it, how to address this problem. Now, in order to do that, what I did is I took just the first top part and make a little model of a transformer, like the lever with the two of the masses and a couple of elements on the right hand side, arming on the bottom here, in such a way that what we want to do is to focus as if we would put a microscope into this and really find out what the solution mathematically is. So what I'm suggesting here is that we will derive the equations as normally, one by one, and you consider deriving this equation, you're going to find out that on E6 is equals to dp sub 6, so the derivative is on the right hand side. So I think right now we have seen that having an equivalent representation solves the derivative form. And right now I would like to explore whether there is other things that we can do once we have the equations of motion or of a system that has derivative form. So that is the next topic that we should analyze, is how to solve it.